Welcome back to 1.2. This is the second lesson of the multivariable calculus series, and we are going to cover cross products. What's a cross product, also known as a vector product? There are two ways to multiply vectors in this course, and the first way was dot product, which we covered last time, and the second way is cross product. So when we cross two vectors, we will get another vector like this right here. This is the formula, and you will have to remember this, but you will also have there is also an easier way to remember this. I will show you later. So A cross B is this chunk, which is a determinant, which I will tell you what that is later, if you don't know already, and which results to this vector right here. And this resulting vector is perpendicular to A and perpendicular to B. So your magnitude, the magnitude of your vector is A cross B is equal to the absolute value, or the magnitude of A times the magnitude of B times the sine of theta this time, no longer the cosine of theta. That is the dot product instead. So that's pretty interesting. The direction of your vector will depend on the right-hand rule. Now, what is the right-hand rule? The right-hand rule is a rule where the first vector that you have, the left one in your cross product, you put your finger on, and the right one on your cross product you curl to, and the resulting vector, A cross B in this case, is the direction of your thumb that your thumb points to. So a good way to visualize is, let's do I hat cross j hat, right? So in this case, I have a coordinate system right here. I hat would probably be something like this, and then j hat will probably be something like this. Remember, I hat is the basis unit vector for the x direction, and the j hat is the basis unit vector for the y direction. So that would be I hat, and that will be j hat. Now if you point your fingers to I hat, and then you curl your fingers like that to j hat, you curl your fingers to j hat like this, the resulting vector that you will get points up. It points up, it doesn't point down. So because it points up, then the resulting vector that you have is actually in the z direction, and it's k hat right here. So that is k hat, which is 0, 0, 1. So k hat. So that is 0, 0, 1 equals k hat. And we can check. 1, 0, 0 cross 0, 1, 0 is equal to what? Is equal to A2B3 minus A3B2. A2B3 minus A3B2, that's still 0. A3B1, so 1 times 0 minus 0 times 0, 0. And 1 times 1, 1 times 1 minus 0 times 0. 1 times 1 minus 0 times 0 is 1. So that is what you get. And actually, I think did I mess up the formula again? I really hope I didn't. I did not. Okay, I didn't mess up the formula. Nice. Very nice. Okay, I thought I messed up the formula for a second. Next. So two vectors are parallel because of the sine theta term. Two vectors are parallel only if they are their cross product is 0, right? Any direction, A cross B or B cross A, it doesn't matter. The cross product is 0, and they are perpendicular only when their dot product is 0 because of the cosine theta term. So remember, this is A B sine theta, and if sine is 0, then they are 0, and A B cosine theta, if cosine is 0, then the angle between them is 90 degrees, which is orthogonal or perpendicular. Note, also important things to know. I don't know if I put it in the last video or not because it's been so long since I've recorded it. But A cross A, anything crossed by itself, or anything crossed by itself that's perpendicular, is 0. So A cross, I'd say A cross KA, which is technically what I wrote right here, is 0. A cross A dot A is the magnitude of A squared. Now if you think about it, that makes sense because it's just multiplying the components together like the distance formula, and instead of the square root, because you're multiplying them together like again, you are getting just the distance squared, or the magnitude squared, right? And if and expanding onto that, A dot Ka is K times A squared, like that, right? Or Ka dot Ka is K squared A squared, right? So it acts kind of like a associative property. Scalars can be moved out of vector products if they need to, and that will be shown in our properties later. So this is the kind of the important thing is your magnitude of A cross B determines the area spanned by a parallelogram with sides A and B. So that's A, that's B. Now if we did kind of a parallelogram sort of thing, A, B, A, B, A, B, and then B, A, like that, where these are our 4 coordinate points right here, then A cross B will give you the area of this parallelogram. I could prove it, but that would take too much time. I don't want to prove it. So find the area of the triangle with sides A, B, and A minus B given 1, 2, 4, and -5, -5, 2. That's my example. Now, I said parallelogram. I didn't say triangle. So how am I supposed to solve this? Well, let's dissect the problem. Let's do a simpler 2D case instead. So if we have a side right here that's A, let's just use red and blue. So A, and then if I have another side that's B, what is A minus B? A minus B is, if we take this vector, we pull it down a little bit, we move it. Can I move it? No, I'd be moving the entire thing. So we can kind of shift this vector. Oh, I'm sorry. We can shift this vector down a little bit. That's minus B, right? So this vector right here, this new vector right here, I'll use purple, is A plus minus B, which is A minus B, right? So that's A minus B. So that's called a tip to tail addition. So then obviously vectors, you can move them. So this is A minus B right here. So those are your sides, A, B, and A minus B. So that's your triangle right there. Now if we expand this triangle, actually let me just remove everything by undoing right there. So that's your A minus B. Now if we expand this triangle so that it's kind of like this, we'd see a parallelogram, right? Oh, I'm sorry. This is a parallelogram. I'm really bad at drawing. Okay, A. So right, this is the parallelogram that we want. That's the A cross B. So these actually split the triangles into 2 congruent triangles because of side, side, side. So A, we have B, and then they both share A minus B. So they're both congruent. So they both of their areas are the same. So because both their areas are the same, and 2 areas of triangles are determined by A cross B, the area of one triangle will be determined by 1/2 of A cross B. 1/2 of A cross B. Right there. So 1/2 of A cross B is what we want to find. And the A minus B doesn't really it doesn't have anything to do with it, right? Unless if you want to find 1/2 of B cross A minus B, which I wouldn't recommend. So or 1/2 times the magnitude of A cross B, I should say, not just 1/2 of A cross B. So what's A cross B? We're gonna have to work it out. So I'm just gonna write this determinant notation out, so that it's a little bit easier to work out. And then this would be what? This would be 2 times 2 minus -4 times -4, that's minus 18. And then 1 times 2 minus, or minus 1 times 2 minus that, which is I think -22. And then plus 1 times -5 minus that, which is -15. So that is your cross product. I hope I got it right. So your answer will be 1/2 times the square root of the distance, the magnitude of your cross product, which I will not further simplify. There you go. That is your answer. Next question. Actually, it's not a next question, it's a next concept. This is called the triple product, or a very, very kind of obscure thing. The vector A dot B cross C. It can also be A cross B dot C. It can also be A cross C dot B. You can move it any way you want, because the magnitude is going to take care of everything. You don't need to worry about the direction. So this determines the volume of the parallelepiped, which is a parallelogram. It's a parallelogram, but you in 3D, right? A parallelogram in 3D. You give it a height, and then you slant it as well. So it's kind of a double slanted parallelogram, but still we have our opposite sides are parallel to each other, and all of the proper properties of the parallelogram that you would normally see. So it's not out of the blue. It's not a shape that it's a shape that you will see, right? We're not gonna have you find the area of a triangle in here. This is just something to know. Probably won't be on the test either. So yeah, but this is the triple product, and the volume of this parallelepiped is determined by magnitude of the vector A dot vectors B cross C. Now, you see me use this notation with the determinants. So in order to make the cross product easier to remember, this is what we use. We use the determinant, right? So there's two ways to compute this, to remember how to compute this easily. The determinant of order 2 for yeah, I'm gonna bring you to a simpler example. Determinant of order 2 is just a determinant with like a 2 by 2. We call it a matrix. So AD minus BC, simple. It's just a crisscross minus, right, plus AD minus BC. It's just a crisscross. So it's not that hard, right? However, determinant of order 3 is a little bit harder because, well, there's more terms. So how do we do this? What we actually do is, you can set it up like this, where you take this and you shift it one more to the right, so you create a copy of it on the right like this, and then this is one way to calculate it that's easy. So you take this, right, you take the product of this line, and then minus, subtract this, right? It's always going to be subtract. So product of this line, or positive product, subtract, like that, and crisscross it like that. So what you will end up getting is, well, A2B3 minus A3B2, which is what we want to get, and then this will be I hat, right? And then now you take minus this line, so minus, and then you crisscross it again, so this and then this, minus J times A3B1 minus A1B3. And then you take positive K, and then you crisscross it one last time. So then you'll get plus K times A1B2 minus A2B1. Like that. So you create this crisscross net sort of thing. It's it's interesting, but it gets the job done, and that is how you would calculate the determinant of anything, not just this vector, but we only care about this vector for now. So determinant of order 3 is calculated like that. Another way that you can calculate it, let me undo everything. Another way that you can calculate it is, this is the I hat, right? You still need the plus minus plus, so this is I hat, so we ignore everything in the row and the column of that. So that's what would happen, right? We would ignore JK and A1B1, and then we would find the determinant of the resulting matrix that wasn't ignored, right? Or we could actually just do this, and then we find the determinant of this, which is, well, in the determinant order 2, it's quite simple. It's just crisscross, so A2B3 minus A3B2, right? So what you'll end up, and then in the J hat, you would do this, and then you'd find the determinant of A1A3 and B1B3, so it would be A1B3 minus A3B1. But of course, keep track of the negative. Yeah, don't forget the negative, and then in K you'll do this, and then find A1B2 minus A2B1. You'll get the same result as the crisscross method, just find the way that you like to use, right? Next, so properties of cross products. These are some properties I don't want you to remember them. I don't want you to remember them, and I don't remember them, especially number 6 and number 5. I don't remember them at all. They're pretty useless, number 6 and number 5. But please remember, number 1, A cross B is negative B cross A. Why does the negative exist? Well, it's because it's the change in direction. If we go back to the first slide, and we did J cross I instead, what we get is negative K. So J cross I is negative K, and if you do the right hand rule, you will realize that there is no way that you can point to the J direction and then point back to the I direction and still have your K vector go up, right? Still have your vector go up. So you have to twist your hand in a way where the K vector goes down, or the resulting vector points down, so that you could point your J, you could point your fingers to the J direction, have them curl back to the I direction. So that just comes from the right hand rule, right? And another thing that's important to know is 3 or 4. 3 or 4. Right? Just know that the distributive property works, but you cannot change the order either. You still can't change the order. So if it's like this, A cross the quantity B plus C, it has to be A cross B plus A cross C. It can't be B cross A plus B plus a C cross A, because because if it's like that, then it will have to be negative, according to theorem 1. And number 2 is useful to know as well, but it's not very well. Number 2 is useful to know, but I already told you, and you can kind of just derive it by yourself. It's not very hard to derive. But 5 and 6 you don't need to know. Just remember 1, 3 or 4, and 2, right? And it's an exercise. If you want an exercise, then you can try to prove 1, 2, 1, 2, 3, or 4. And if you're really swell, then you can prove 5 or 6 as well. But I'm not going to try to do that today. Let's do some problems. I will give you a few seconds to pause and then do the problems. I'll give you a few seconds to pause and do the problems, and the few seconds starts right now. Did you do the problems? I'm gonna go on without you anyways. Question 7 of this book. I use the Stewart Multivariable Calculus book, and you should get it, or you should get another multivariable calculus book that covers all of the content that we're going to cover, which I think I have in my Intro to Multivariable Calculus book or video. I'm sorry. Yeah, so find A cross B. Now, these are, in terms of variables, might look a little bit scary, but they're really not that scary at all. I'm going to use the copy method. So T1 1 over T. I'm going to use the method where I copy it over to the left side like this, and then we will calculate it. So what's your resulting vector? A cross B is swish swash. Swish. Oh god, I'm sorry. Swish swash. So 1 times 1 is 1, minus 1 over T times T squared is T. Next, swish, squash, swash. So 1 over T times T squared is T. Or, well, this is negative, so 1 over T times T squared is T. Don't forget the plus minus plus. There you go. So negative 1 over T times T squared is T, minus 1 times T is T. So 0. And swish. That's so scuffed. Swish, swash. T squared, T times T squared is T to the 3rd power, and 1 times T squared is T squared. So that is your vector right there. Pretty easy, not very hard at all, right? Use the right-hand rule to determine whether I cross K is J or negative J. I want to give you a few seconds to try that, and I'm going to try that myself. Okay, what did you guys get? You guys should have gotten negative J, not positive J. I can prove it. I can do the same method. We're going to do it quick this time because there's a bunch of zeros. So I, J, K. I is 1, 0, 0, and K is 0, 0, 1. So it will simply just be 0 times 1 minus 0 times 0 is 0. Minus 1 times 1 minus 0 times 0 is negative 1. And then plus 1 times 0 minus 0 times 0 is 0. So it's just negative 1 in the J direction, which is negative J. If you put your hands in the I direction, it's a little bit hard to put your hands in the I direction, I'm going to be really honest. And then you curl it up. So if you put your hands, I'm going to say towards you, and if you curl it up, you'll realize that it's pointing left. And in the right hand, in the system of coordinates, J or Y is pointing right, not pointing left. So that's why it is negative J. Find A cross B dot B. This might seem a little bit daunting at first until you find a trick, and I'm going to give you a few seconds to have you find that trick. Did you find it? The trick is that A cross B is always perpendicular to A and B. A cross B is perpendicular to both A and B. And when something is when there's a vector perpendicular to B, so perpendicular or orthogonal to B, dot with b, you will always get 0. So this is always 0. And we could also prove it because the cosine of 90 degrees is 0, or well, pi over 2, cosine of pi over 2, or 90 degrees is 0 degrees. So if you cross A cross B is always perpendicular to A and B, and in fact every single linear combination of A and B, which we'll see in the next slide. But if it's perpendicular to B and you dot it with B, then it's always 0, right? If you dot it with A, you also get 0, right? So if I was evil, I would do A cross B dot A dot B, and it would still be 0. So I'm sorry. Next question. This is a question that you will probably see on my test right here. Given the vector A, I bold A and I bold B because that's how the textbooks do it. You could also just put an arrow on top of it. I like that more. Find 2A minus 4B. Very easy. Doesn't really take that much effort at all. Easy 2 points. Just 2 times 2 is 3. Negative 1 plus 4 times, or I'm sorry, minus 4 times negative 1, 1, 0. Doesn't take that much effort at all. Just do that. And usually you shouldn't simplify, but we're going to simplify anyways. That will give you 8, negative 2. No, not negative 2, I'm sorry. Positive 2. And then negative 2. Wait, am I smoking something? No, I'm not. Okay, that's negative 2, definitely. Okay. I'm not smoking anything. Nice. Find a vector perpendicular to 2a and negative 4b. So a vector perpendicular to 2a and negative 4b, you should already know how to do this. It is simply just a cross product, right? So that's a very important thing to know. A cross b will be both perpendicular to A and to B. Or, yeah, in this case, 2A cross negative 4B is always perpendicular to 2A and negative 4B. So, 2A and negative 4B is, well, 2A is 4, 6, negative 2. And then negative 4B is positive 4, negative 4, 0. So if you cross them together, I, J, K, 4, 6, negative 2, 4, negative 4, 0, equal to 6. That's positive 8. No, it's negative 8, because minus 6 times 0 minus negative 4 times negative 2, and then 4 times 0 minus negative 2 times negative 4, or negative 2 times 4 is negative 8, but minus, so positive 8, but then J has a minus, so it's negative 8, and then K is 4 times negative 4, positive 4 times negative 4 is negative 16, minus 4 times 6 is negative 40. Right? I think so. Negative 40. Show that the resulting vector obtained in part B is also perpendicular to 2a minus 4b. How do we show that vectors are perpendicular to each other? Go back to page 2. Two vectors are perpendicular if and only if a dot b equals 0. So let's do a dot b. Now what's a? A is your 2a minus 4b. And then your b is negative 8, negative 8, negative 40. So we can calculate this out. 8 times negative 8 is what? Or, in fact, in my test, if you just do this, you will get the point. Right? That will just get you the full credit. But if you want to be very, very sure, then that you didn't do it wrong, then you would do that and realize that it's negative 80 plus 80, which will give you 0, and that is the right answer. So that's gonna be it for today's lesson and practice of the cross section. If you guys are using the same book that I am using, then you should do some of the problems in that book. Obviously, you should practice your cross product with the first 7 questions. In the book, it's Multivariable Calculus Brooks in 2012 by James Stewart, and you should also try to do some of the problems like the ones in like 15 through 19, and you should also do the problems 29 through 36 to find volumes of parallelepipeds, and you should also do some of the problems from, not all of the problems because that would take really long, 39 to 40, I'd say 46, right? I don't want you to prove anything, although if you want to, I'm not going to stop you. Yeah. So that is it, and I will see you next time for equations of lines and planes.